lecture, we look at the Blin-Phong model, which is a modified Phong model for shading. Surfaces of objects have their material properties to interact with light source properties. There are 9 absorption or reflection coefficients. 3 for the 3 colors, the red, green and blue, and 3 for the ambient, diffuse and specular components. And there is one shininess coefficient, alpha. The ambient term of the light is the simplest to calculate. The intensity of ambient light IA is the same at every point on the surface. Some of this light is absorbed and some is reflected. The amount of reflected light is given by the ambient reflection coefficient RA, which is equal to Ka. The value of Ka is between 0 and 1. Thus, the ambient reflection is Ka multiplied by La. La is the ambient component of the light source. Now let's look at the diffuse term of the reflected light. A perfectly diffused reflector scatters light equally in all directions. Such a surface appears the same to all viewers. However, the amount of light reflected depends on both the material and the position of the light source relative to the surface. So the diffuse reflection is proportional to cos of the angle theta, and theta is the angle between the normal and the incident light. Normal is the surface normal. Cos theta is basically the dot product between the L and N vectors. L is where the light source is and N is the normal of the surface. So we can write ID is equal to LD RD, and replacing RD with L dot N KD. KD is the material property of reflecting diffused light, and then incorporating the distance term in it. So KD is here, it is divided by the quadratic term, which is a function of the distance d from the object, and 3 constant parameters defined by the user, and plugging in Rn over here and Ld here, we get the final equation of the diffuse reflected term. Let's look at how to compute the specular component of the reflected light. Specular reflection is mirror-like reflection from smooth surfaces. Phong proposed an approximation to this reflection, which is done with a slight increase over the workload already done for diffuse surfaces. So specular reflection is equal to LSRS, which is equal to the specular component of the surface, the specular component of the light source, and cos of phi raised to the power alpha. Phi is the angle between R and V, which is the vector to the viewer and the vector in the perfect mirror-like reflection direction. Now this can be finally written as Ks ls R dot V, where cos phi has been replaced with the dot product of these two vectors raised to a power alpha. Now we can see that if R and V are closer together, this angle is very small, the value of this component will be very high, and hence the surface will appear really specular. To get the final shading at a point, we will need to add up all the terms that we have studied. That is the diffuse reflection term, the specular reflection term, and the ambient reflection term. Note that we have skipped the distance terms here. We have not written them for brevity. And also note that the diffuse and specular components depend on these vectors, whereas the ambient term does not depend on any of these vectors. And finally note that only the diffuse and the specular components will have the distance terms for attenuation, and the ambient term does not have that component. And we will have to calculate this equation 3 times, one for each color, for red, green and blue. And if we had, say, 2 light sources, we will have to do 3 multiplied by 2 is equal to 6 calculations. So 1 for each light source. And because every light source has 3 colors, we will have to do 3 multiplied by 2 is equal to 6 calculations. To compute the shading value I in the previous slide, we need to know those vectors in the model, all 4 of them. The normal vector n is determined by the orientation of the point P. Vector L and V are specified by the application as the light source and the viewer locations. And we can compute R, the vector of perfect reflections from L and N. So we can show that the vector of perfect reflection R will be equal to L dot N multiplied by N into minus L. So we don't need to know how to derive this equation, but we just need to consider that this amounts to a dot product multiplied by N and a subtraction of the L vector. The specular term in Phong model is problematic because it requires the calculation of the reflection vector v for each vertex. Blin suggested an approximation using the half-wave vector that is more efficient. This is referred to as the modified Phong reflection model, the Blin-Phong model, or simply the Blin lighting model. The half-wave vector is halfway between the L and V vectors. We must know the L and V vectors as the position of the light source and the viewer respectively, and hence we can easily compute the half-wave vector using this equation, which is more efficient than to compute the R vector. Using the half-wave vector h, we can replace v dot r raised to the power alpha by n dot h raised to the power beta, where beta is chosen to match the shininess of the material. Note that halfway angle is half of the angle between r and v if the vectors are coplanar. And the final Blin lighting model becomes like this. So where we write n dot h raised to the power beta for the specular term. Note that we have again skipped the distance terms over here. The Blin lighting model is the default shading model in OpenGL.